Sorry. So welcome to this interactive session, unfortunately on Zoom, on this lecture 10. So what we would like to discuss quickly today is first answering some questions which have been posed by some of the students, and then go through some examples of exams from last year, so that you can get a little bit of feeling what the exam questions could be. First of all, could somebody show me that everything, you can clearly hear me and see me? Great. Thanks. Then I would propose I directly go with two questions which have been asked to me through the chat. The first one, I will directly share this with you. The first one was about virtual control input, what this is about. So in principle, it sounds much more than it is. As you can see here on this slide, on the left, I will make it big. So as you can see here on this slide, we have for roll, pitch, and yaw, decoupled systems. This is very nice with quadrature, at least as long as you are around hover. And now what we want to do is actually to simplify just the equations. So we actually define a virtual control input, the difference of the omega squares. So you can see here, this is the same equations as on the other side, just u is then defined by this difference between the different rotational speed, and it's the same for pitch and yaw. And in principle, this is quite simple. It sounds like something very fancy, but it's just to simplify somewhat the equations. And this you can do because this whole system is largely decoupled. Now, there was a second question about the main rotor and the forces acting on the main rotor. This is this slide. Make it big. So the question was here: how do you come up with Vg, which is equal to omega rotate of the rotor multiplied by r? This is actually also pretty simple. So imagine this is a blade of a rotor, of a quadrature or whatever helicopter, and the distance from the center to the element you're looking at, typically you are doing this blade elements, only a small small part of the wing, is the speed of this part is equal to rotational speed of the main rotor multiplied by the radius at this point. And this gives the forward speed at this point. Of course, you have to realize that it will vary over the rotor. In the center, you have zero speed in principle, and at the tip blades with big helicopters, typically you are close to sound speed. With quadratures, you are much lower, but you have a large variation. And this is also what you can see typically with some of the, I don't know why I move some, with some of the quadratures that they have rotors which are actually torted around. So because you want a different angle of attack dependent on the velocity as a function of the radius. Now I've seen there was just another question about in what kind of situation would the decoupling approximation fail. In principle, it fails immediately if you are not in hover. But in a lot of cases, you can actually neglect the influence of this coupling. But of course, the faster you go, the more dynamic you fly, the more you have to consider the coupling between the different systems. And of course, there is even, as we have seen in the for the forces generated by the rotor, which is actually here, for example, you can see that there is also some, not only the thrust and drag torque, which is the ideal case, but as soon as you're moving forward, you have different speeds coming onto the rotor of the helicopter. because you are moving in this direction, so you have different speed on propeller if it's in this situation or this situation, and you have to consider this. And so this gives also some effects. But these are typically secondary effects, so as long as you are moving slowly, you can still actually be pretty precise with the simplification, the decoupling. And of course, some of this decoupling is then taken care by the controller. So if you have, for example, a position controller, the controller will actually correct the side effects. But if you really fly on high dynamics, as you have seen in the lecture, like for example, if you want to play ping pong with a helicopter, you have to go a little bit further and consider these elements. Yeah, there was a question about the set direction. Yes, typically we use the set directions towards down, but in principle there is not a fixed convention. So in principle you can select whatever you want. But in most systems you use actually the set direction around the rotation of an axis or of a rotor. There is some more questions coming in, so I have to see if I can follow all of them. Let me quickly see. There was another question. So there was a question about this two terms, U induce and VP. VP is mainly the element which is coming from the general flow through the rotor, and V induce is actually an element which is coming from the propeller itself. So this is typically the smaller part, but they can be calculated by the two different elements. So if there is no further question, but you can still put questions in the chat. So I will quickly go to the examples of exams. So the exams are typically not so difficult if you understood the basic elements, and there is calculations you can do mainly by hand. So let me open this part and share it with you. So let me quickly, and if there is something not appearing appropriately, you tell me, or actually somebody should unmute and give me a sign. So let me go through some examples. So first, this is an example from previous years. Imagine that you have this quadrotor with these 4 propellers, which are counter-rotating actually as it's designed here. And you bought a helicopter and you would like to verify the efficiency and of the propeller. So first of all, you would like to calculate the rotational speed in hover, and you have the given properties, as you can see in the table. So it's the mass, the thrust constant, which is the constant of generating, or the constant which is multiplied then by the rotational speed of the individual rotors. You have the drag constant, but we will see that the drag is neglected, and we have, of course, the gravity acceleration, and we are on Earth, which 9.81 meters per second square. Now, if you look at the first at the first equation, so this is in principle pretty simple. So in order to hover and stay in place, you have to generate the force which compensates the weight of the whole quadrature. So you have the mass, you have the gravity, mass multiplied by gravity, divided by 4. And the reason why we divide by 4 is because we have 4 propeller. We assume that all are equal. This is the thrust force you have to generate in order to hover. And of course, on the other side, you also know that the thrust force is actually the thrust constant multiplied by the square of the propellers. And again, we assume that all the propellers are exactly the same. Some are counter-rotating, so they're compensating the rotation around the z-axis. And based on these two equations, you can easily calculate then the rotational speed of the individual propellers. Now, the second question is if we want to have an acceleration upwards. So we would like to accelerate our helicopter upwards, and we neglect the drag force, and we assume that we can instantaneously generate or change rotor speed, which is, of course, in reality not fully given. Oh, this is, sorry, I was wrong with the question. So you want an acceleration along the x-axis, not so meaning that the acceleration should be in this direction of the propeller, so towards x. Now, for getting an acceleration, you can actually, the force you have to generate is the mass multiplied the acceleration in this direction. So m multiplied by ax. You know the mass, you know the acceleration, which is given for this exercise, and then you can calculate the force in x direction. You also can calculate easily the force in z direction. This is the meaning that you want to hover and you don't want to change in z direction, which is equal to the mass again multiplied by g. And then the angle for this acceleration actually is given by the two forces. So you have the arctang of the force x in x direction to z direction is equal to the pitching angle, which is asked in this example. Now I go forward to a second example, which are quite similar. This is from another year. Again, you have the mass quadcopter given with the mass and the thrust constant, accelerator vector, but you have additionally also a given maximal propeller speed and a minimal propeller speed. This is quite often given by the propeller. At very low speed, there is an issue that you cannot measure the speed correctly because they are have no specific sensors. Typically, they're measuring the rotational speed by induced currents, and so they are not really running smoothly at very low speed. And of course, the maximum speed might be limited by the converter, by the propellers themselves, and so on. So first, it's again the first thing is a movement in z direction, but here we don't want to hover only, but we want to actually move against gravity. And the second element is the motion, the torque, which we can generate with the change of the rotational speed. Let us have a first look at the ascending acceleration against gravity. So in order to get this, we have not only the gravity, this will be for hover, but we have an additional acceleration, which is 1 meters per second square. And so the total acceleration is gravity plus the gravity, the acceleration we want to accelerate upwards. So based on this, we can again calculate the force, which is has to be generated for this acceleration. And then, of course, the propeller thrust has to generate this force. We have again 4 propellers. We divide this force by 4, and so we get the propeller thrust, which is 1.35 Newton. And then we can again calculate the propeller speed, by the propeller thrust multiplied is equal to the propeller rotational speed in square multiplied by the thrust constant, and then the square root of the propeller thrust divided by v is then the rotational speed of the propeller. So it's quite similar to the example we have seen before. Now, the second example is the question about calculating the maximal body torque in the three torque direction mx, my, and z. The whole system can achieve while still respecting the rotational speed. So we have the rotational speed which is given, so the maximal thrust of a single propeller is then again the thrust constant multiplied by the maximal propeller speed which is given in the table. The minimal thrust is the same but multiplied by the rotational speed, minimum rotational speed. So you have then the maximal and minimal thrust force which can be generated by a single propeller. Now in x and y, you can actually, if you want to move or generate a torque in x and y, you actually use only the two propellers which are on the other axis. So if you want to calculate the rotation around this x-axis, you have to look at omega 1 and omega 3, and you just plug this in. But of course, you have then the force will act on a distance, the distance L, from the propeller to the center. So you have then L multiplied by the difference of the two thrust vectors gives you the torque you can generate in X, and it's exactly the same for Y. And in the Z direction, you have actually the torque which is generated by the difference of the rotational speeds. So you have then the maximal you can actually have if you have the difference from propeller the two propellers alleviated, and so at the end you can also calculate the maximal torque around the z-axis, around the rotational axis of the system. Now, as the next or the last example, we have something similar, but we have here not a quadrotor, but a helicopter with 6 propellers, so a hexacopter, where we have again also the arrangement that always 2 pairs of rotors are rotating against each other or in counter-rotating speed. So in general, you don't have a rotation around the z-axis which is generated. Now we have then also the inertia given for this system, which you can see here, which is typically equal to around x and y axis, but it can be different to around z axis. As you can see it here also in this example, we have the arm length, which is the point or the length of the arm where the propeller is. Now the question is, we assume that this hexacopter is hovering in steady state and all rotors are rotating at the same speed. What is the rotational speed to hover? This is quite similar as we have seen before. So in principle, the hover force is the gravity multiplied by the mass. Then the propeller here, instead of 4 propellers, we have 6 propellers. So again, the thrust, which is generated by the 6 propellers, 6 multiplied by the thrust constant and the omega square. And then we can again calculate the rotational speed. Now, the second question is about the body angle if, for example, you have one rotor which is breaking down. And we assume that just the rotor flies away or whatever. So we have one of the rotors which is not generating any force anymore. And then we would like to have the body angle and linear acceleration of the system after it lost a rotor. Or it could also be just stop one rotor. There is in this question is also, if you would have not answered the first question, you would give a rotational speed, but typically you take the rotational speed from the system above. So now if you look in the equations, which would be a little bit different than the quadrotor, but again, there is always some propellers which give an influence on some directions. There is also some decoupling. And of course, the example is selected simply enough so that you can easily calculate this. So we have the propeller 2, which is this one, which is broke. This one, which is broken. So we have this one which runs. All others are in symmetry and are at the same speed, so they will have no influence on any torque or movement. So then we can make the calculation actually for the rotation around the x-axis, which is this axis, which is equal to actually only one propeller acting. This is only propeller 5 because propeller 1 is not acting anymore. And if you take this equation, which we have seen in the lecture, you can then easily calculate the acceleration around the Z, which is equal x-axis, which is seen here. Now for the rotation around the Z direction, or in absolute body frame, but here we have it aligned, we have again the inertia around the Z-axis multiplied by the acceleration around the Z-axis is equal to actually the torque generated by the propeller. And this is then, of course, here you have to use the drag force, because the drag force is generating this rotation. And then if you plug this in, you can also again find the rotational acceleration around this axis. So we have then a rotational acceleration, which is given in total. We have two elements in a vector, which has a component in x direction and in z direction, nothing in y direction, because in this y direction, around the y direction, there is no change, because the propeller which was failing is on the y direction. And based on this, you can then also calculate actually the acceleration in z direction, which is equal to the sum of all the rotational speeds multiplied by the thrust force. And if you plug this in, you have the acceleration. And the acceleration is only in z direction, because at this moment you have no inclination. But of course, what would happen in the next step in the time scale, the whole rotor will actually skip a turn, and then you will have also accelerations in other directions. But at the moment of hover, you are totally horizontal. So the first moment you have no acceleration in x or y direction. But you can see then, of course, if you want to describe the model in a time series or with an evolution of time, it's getting much more complex. So this is some examples. So this gives you hopefully a feeling about what type of questions you might have to answer. And so I'm now going back to the chat and see if there is some additional questions, and give me some time to go through it. So there's one question: if you could revert the rotation direction of propeller T. Let me quickly see. This is 2B. Oh yes, now I understand. I got the probably point. Typically, the propellers are only rotating in one direction, because otherwise they will not have the full efficiency. There are some systems where you change really the rotation. It's in principle feasible, but you have to go through zero. This is one element, but the more critical element is that you need then a symmetrical rotor. Whole aerodynamic will not be as good. And going through zero is very difficult for the control. So in most cases, you have always a positive or one, you rotate only in one direction. And this makes also sense because the propellers have to rotate anyway at a given speed because you have to compensate the gravity. So you will actually vary the rotational speed around the value which is needed to be at hover. There was one question about why do we not take the gravity into account. I don't know which to which question this is related. I'll probably go forward to the next question, which is slide 47. There's a question, why is the control surface A3 not also at infinity as A0? In principle, you're correct. So in principle, also E3 is at infinity. We assume, but of course, we can typically say that infinity, it has not to be fully at infinity because at a distance, a certain distance of a couple meters, typically the local flow of the rotor has no influence anymore. Yeah, there is a question about the hexacopter with 6 rotors. Sometimes we have even 8 rotors. There is a couple of advantages with having more than 4 rotors. 4 rotors is the minimum that you can actually generate hover or actually forward backward speed and can control the rotation around the center axis. If you have 3 rotors, you can not control all the 4 main elements you need. Now with 6 rotors, you have the advantage that typically you can have a better coverage of the surface covered by all rotors together. So ideally, you would like to have a helicopter which uses all the size, the outer diameter. Inside, you should have as much propulsion or thrust generated. And so with 6, you can do more. And of course, with a hexacopter, you can also compensate if there is one propeller failing. So in principle, there is even work at ETH which was done in this direction so that you can actually still correctly hover if one rotor is failing because you have still enough control power. But you have to adapt the controllers. You have to first identify this. By the way, it has also been shown that in principle you can have a somewhat safe landing even with less than 4 propellers, but of course you have then probably a wiggling around the center axis, but you can still land if you adjust the propeller. For the hexacopter, there is a question about the hexacopter, why we compute acceleration Z direction. Of course, we just okay, this was the question linked with this. This was follow-up. So then there's this question to slide 31. All right, here, go to this 31. So there was this question: why do we use them if they are met to 0 at hover? Of course, at hover you have to control hover. In principle, in the ideal case, all the forces will be 0 and U1 will be mg, but in reality, of course, you have to control. So this describes the dynamic of the system, and you will control around, in hover, for example, around the 0 axis. So you have to calculate the forces generated by the propellers if you deviate, and how you can actually bring it back to hover or to 0 position. There was one question about the yes, about this elements for the controller. So of course, which was not detailed in the lecture. You always have to have a knowledge about the angles and the position of the whole system. And for the angular control, typically you have the IMU. IMU is giving you accelerations in X, Y, Z and rotational speed around the 3 axes. So this is directly then considered as used as the input. Now, for the position, if you want to do a position control, you have the acceleration, you can double integrate, and then you would have the position, but you have an offset, which you cannot calculate. So for the position control, you need actually a position measurement. And this is in free space, typically GPS giving you this information. Or in a system which is flying indoor, we have typically laser sensors or cameras on board, which give you in a given reference frame the position X, Y, and Z. And of course, this you have to use then in the whole control. So control needs the input, and this is typically a measurement, and very often the measurement itself is only a challenge. So there is some questions I probably not fully understand about this quadrotor or the hexacopter. Of course, if you lose one propeller, you have 3, which are 5, which are just still helping us to hover, but one losing. So you have to adjust the propeller speed so that you could still hover. But then, if you want to really control it, you have to have really a different control. It's really a different model because you're doing one rotary. But in general, you can still calculate the up force, and this is what is done in the example or the exam, so that you have at this moment, at exactly this moment where you lose the propeller, what are the forces acting on and torques acting on the system. So there is a question about the exam. So the exam will not go deeply into control. So it's not a controls course. It's a dynamics, more robot dynamics course. So you don't have to have a controller layout, but you have, of course, to understand what you could do with a controller, and the examples or the exam will be similar to what you have seen here. So you can vary, for example, the number of propellers that we will always be around, hover or whatever, so that the calculations get not too complex. But you could probably also imagine what would happen if you have only 3 propellers, or if you have 8 propellers, or similar different arrangements. So there's a question on page 38. Should there be a minus on equation? So of course, this minus and plus is always a question how you define your system. So as you can see here, we have here a plus. I think it's correct, and you can see then here that we have the u, which is the control, which is the thrust vector multiplied by these 2 angles. And here is the minus. So the feedback has the minus sign involved, and not the u directly. So we have defined more or less the positive force generated by the thrust is going the positive direction of our coordinate system. But you could do it also the other way around. So always all these signs, you have to define it, and you have to be consistent, and then it will work out. Okay, so I see that we are towards the end of the questions. So please feel free also still put questions in Piazza, so that we can respond there. I hope you got first introduction to quadrotors, and especially also that the whole robot dynamics is really playing an important role once you want to start to control this. I think it's also important to understand, if you want to do really acrobatic maneuvers, very fast maneuvers with a system, then you have to go beyond what we have seen in the lecture. This would need more thorough, but in principle, it's still the same equations, and you can build exactly on what you have learned in robot dynamics. So thanks very much for your interactions, even if it's a little bit strange that you will only have feedback through chats. I would prefer to have your voices, and I hope you will have a good continuation of project. Thanks very much, and bye-bye.